Hey guys, welcome back to my channel. I am Anay Gupta and I'm so glad to have you here today. For all those of you who have your physics practical exam tomorrow, you are exactly in the right place. I personally am an India topper for physics, chemistry, and a world topper for mathematics at the AS level. Additionally, I scored All India rank 1 at the AS levels. At my IGCSEs, I was world topper for mathematics and ICT alongside scoring best across India rank 3. So guys, I do have pretty much an idea about the CAI universe. Last year, I was sitting this exact paper, May June 2024 9702 33. And today, we will be taking a walkthrough of that paper to discuss the insider secrets of how to ace the physics practical exam. Now, it took me some time to collate these secrets, but luckily for you, you have the world topper right here who's gonna spill out these secrets. So make note of them as I write down the exam again after 1 year. Through the course of this video, we will also be making notes of key points in the text box above, and please make a note of them so that you don't forget them on exam day. Without further ado, let's get started. Okay, so we all know that the physics practical exam contains two questions, a long experiment and a short experiment. For us, we investigated a balanced meter rule, which is basically a pivot based experiment. However, you could be given something like oscillations, electricity, pulleys, springs measuring water levels, or even heat based experiments. Whatever they are, all you have to do in question number 1 is read the question to the T and record your values, plot your graphs, and calculate your values with utmost precision, accuracy, and technique. Alright, let's get into this question. You have been provided with a meter rule and some masses. Place the masses on the rule as shown in figure 1.1. Place the 100 gram mass at one end of the rule and the distance between the 100 gram center of the 100 gram mass and the 50 centimeter mark on the rule is A. Measure and record A. Now, the first instinct might be to record A as 50 centimeters, but if you look closely on the diagram figure 1.1, we notice that the value A doesn't really start from the left hand side of the rule. However, it starts from the center of the 100 gram mass. So if you just think about it, A is basically nothing but 50 minus the radius of the 100 gram mass. So we weren't really given any vernier calipers or micrometers to measure the radius of the 100 gram mass. So how did we improvise and find out a makeshift value for the diameter of the 100 gram mass? Now, we all know that there is a 50 centimeter mark at the midpoint of the ruler. The end on the left of the 100 gram mass aligns with the 0 point on the ruler, right? So what I did was I simply found out the reading for the right side end of the 100 gram mass, which incidentally happened to be 3.8 centimeters. Now I know the diameter is 3.8 centimeters, so the radius will be the diameter divided by 2, which will be 3.8 divided by 2, that comes up to 1.9 centimeters. Now if I just substitute the value of r into my equation, I get that as 50 minus 1.9, which comes up to 48.1 centimeter. Now, in your examination, you don't really need to show so much calculation, especially for a one marker here in the first place, because if you have written a value less than 50 centimeters, somewhere between 46 to 49 centimeters, then I think Cambridge knows that this is what your thought process has been and they will award you a mark for that. So we simply record our value 48.1 centimeter. Now, two things to take care of. Our first two key points. Number one is our readings have to be to the least count. What does that mean? So our ruler measures to the nearest 0.1 centimeters, right? So our ruler measures to the nearest 1 millimeter. That means that our value over here is going to be to one decimal place. If we used a vernier caliper, for example, it would measure to the nearest 0.01 centimeters. Hence, our value would be to two decimal places. If we used a micrometer, our value would be to three decimal places, and so on and so forth. So whenever we are measuring a value, okay, we have to take care of the decimal places of our value, okay. And the second important point here is to record the units. Okay, without the units, you forget the units, you forget the mark. Okay, you instead of centimeters, I could write meters, I could write millimeters. Okay, but it has to be a metric unit of length. That is very, very important. Okay, let's move forward. Place a 10-gram mass so that its center is distance a from the 50 centimeter mark on the rule. So we have placed a 10-gram mass. So if this is 50 centimeters, then the 10-gram mass center should coincide with approximately 98.1 centimeters on the meter rule. So whatever the 98.1 mark is, you place the 10-gram mark over there. Secure this mass in place using the adhesive putty. This mass must remain in place throughout the experiment. So I simply put up putty over here. Place 7 10-gram masses so that their centers are above the 50 centimeter mark on the rule. So I just stacked 7 10-gram masses as we can see in the diagram. Let's move forward. Transfer n of the 10-gram masses where n equals 4 from the center of the rule onto the 10-gram mass near the end of the rule. So we had 7 10-gram masses over here. We just transfer 4 masses from the center over here onto the right hand side over here, as we can see in the figure 1.2. Carefully place the rule and masses on the pivot as shown in figure 1.2. Adjust the position of the rule on the pivot until the rule is balanced. The distance between the pivot and the 50 centimeter mark on the rule is y. Record n and y. So what we basically have to do is, first we put the rule, put the masses on the rule as we have been seeing in the diagram. After that, I hold the rule with one hand, and with another hand I slide the pivot and move it until I reach a point where the rule is hanging parallel to the ground. Okay, now it will obviously be very difficult for me to get a situation where the rule is perfectly balanced. So yeah, I can assume that the pivot is at its perfect point when I leave the leave the ruler. The ruler stays in the air for about 5 seconds in its perfectly horizontal position before it tips to one side of the ground. Okay, so if it is just hovering, if it is resting on the pivot flat for about 5-6 seconds, then yes, you can be rest assured that you have placed your pivot at a appropriate position. Now record n and y. So n has already been given to us. N is equal to 4, and y, we can calculate y with, say, let's say that this is at the 50 centimeter mark, and let's say that this is at the 40 centimeter mark. Okay, so y will be 50 minus 40, the distance between, that would be said 10.0 centimeters. Okay, when I did the experiment, I found y to be 8.7 centimeters. Again, our two key points are adhered by. We have recorded the value of y to in the proper units, that is centimeters, and to one decimal place, that is the least count of our ruler. Okay, now another very exciting advice that I give everyone is to use averages. Okay, so our third point here is repeat and average. Now what does this mean? Okay, let's say, take this statement for instance. Let yi be the ith value of y for I belonging to natural numbers. Okay, now this statement is a little complicated, but if you write this statement, rest assured the examiner will be blown away by your mathematical and scientific fluency. What this basically says is that we are repeating the experiment multiple times and then we will average the value of y. Okay, so let's say that when I first did this experiment, I found y1 as 8.8 centimeters. Okay, then I just moved the pivot away and then just sort of tried to balance the pivot again. So then I found the value of y2 to be 8.6 centimeters. Now, these small discrepancies could be for various reasons. For example, the wind, or how the air conditioning is working in the classroom that you've been working in, or for example, you were putting different amount of force when you were supporting the ruler with your hand, and when you let that go, how that affected the ruler is also a consideration that you need to take. So different little slight factors here and there could affect your readings by, say, a 0.1 0.2 centimeters here and there, and that is what we're telling the examiner, that we are trying to ensure maximum accuracy. So when I repeated the experiment the third time, I got it as y3 equals to 8.7 centimeters. Okay, Now, after this, what should I write? I would say let ya be the average value of y. So how do I calculate the average? I simply take the mean of y1, y2 and y3. So that would be 8.8 plus 8.6 plus 8.7. Okay, divided by 3. So if I just put that into my calculator, I get that as 8.7 centimeters. And that is how I get my value of y equals to 8.7 centimeters. Now, in this question particularly, if I didn't use averages or repeats, I wouldn't be penalized because my values of y are pretty close to each other. So the human error is pretty insignificant. But for example, if you have an experiment such as oscillations, okay, in that case, you need to use averages because the human error is quite significant and your values of the time period would be very far apart from each other. So you have to use this similar annotation and calculate your average value for the time period. Okay, now the next key point that we have is measure for many. What does that mean? So if we have something like oscillations where the values that we are measuring are very small, right? About say 1 second or 2 seconds, in that case, the human error or the reaction time becomes very, very significant compared to my value that I'm getting. So what do? I say let t be the time for 10 oscillations and let small t be the time for one oscillation. So I will carry out the entire procedure to calculate capital T's average value. Okay, because that mitigates my reaction time's significance, or that mitigates the percentage uncertainty in my value. And after I do all that, okay, this is just one oscillation, okay, the small t. Please don't mistake the legibility of the writing that I'm doing. And then we use the formula small t equals capital T divided by 10 and we get our value for small t. Okay, so that is a way that we ensure maximum accuracy in our readings. If we get a question or if we get a possibility of measuring for multiple values, then yes, we need to use this method. If you skip either of the methods and say an oscillation based question, then you will be dropping marks for sure. But here I thankfully did not need to average or multiple for measure for multiple values. Okay, next question. Change n by moving some of the 10 gram masses from the center of the rule onto the 10 gram mass near the end of the rule and determine y. Repeat until you have 6 sets of values of n and y. Record your results in a table. Include values of 1 by n and y by n to 3 significant figures. Okay, now if we read the question very carefully, it starts with change n. That signifies that n is our independent variable, and it ends with determine y. That means we have to measure y, right? So that makes y our dependent variable. Okay, so as a rule of thumb, independent variable goes to the left of the table. Okay, independent variable goes to the left of the table. Key point number 5, independent variable goes to left of table. Now, so we start with n, y, and then our calculated values 1 by n and y by n. Now, because the y values are so close and I do not need to repeat the experiment again and again for this particular experiment, I have not included the y1, y2, y3. Otherwise, you can include columns like y1, y2, y3, y average, stuff like that as well, to show that you are averaging and improving your accuracy at each value of n. Okay, if you get an oscillation based question, you have to have columns for t1, t2, t3, t average, and then a small t value as well. Okay, now after I have my column values or the column variables, I will need to allocate units to them. So n is just a number, it has no units. Y is a length, so y has the units of centimeter. 1 over n has no units, and y over n has the units of centimeters again. Okay, now I have my columns here. It's pretty much well made here. Okay, now n, if we just see, we have 7 10 gram masses. So I can either transfer one mass, I can transfer 2 masses, I can transfer 3 masses, all the way up to 7 masses. So n can take a value of 1, 2, 3, 4, 5, 6, and 7. Okay, n can take any value out of these numbers. So my next key point that we come to, okay, I think the key points just froze. I'm sorry for that. But if you just see, the third key point was repeat and average the entire uh, entire this thing, the annotation that we did there. The fourth key point was measure for many. Okay, measure for many when there is a possibility of high human error. The fifth point was independent variables to the left of the table. And now we have our sixth point, that is good range of independent variables. Okay, before I continue, I just want to apologize, guys. This entire time while I'm filming the video, my computer has given me a lot of troubles. You know, one time the mic was disconnected, my camera was glitching, my OS was also glitching a little bit. So if there are some problems with, say, the video quality, the audio quality, or some little technical problems like that, I hope you can please ignore that and focus on the physics aspect, the content aspect of this video. Thank you. Let's continue. Okay, so good range of independent variables. Now, what do I mean by that? So if we have the opportunity to have 1, 2, 3, 4, 5, 6, and 7 as values of n, we will want to take as extreme values of n as possible. So I want to take the lowest possible value and the highest possible value as well, right? So I will take values of 1 and 7 and then choose any 4 values out of the remaining 5 numbers. So here I take values of 1, 2, 3, 5, 6, and 7, for example. I made this mistake in my board exam. I took 1, 2, 3, 4, 5, 6, and I was penalized 1 mark for that. I don't want you to repeat that same mistake, and so please take the extremest values of the independent variables. Okay, so for example, if there's a pendulum string, okay, that has a length of 100 centimeters. Now, you obviously can't take the full 100 centimeters because you need a little bit, you obviously can't take the full 100 centimeters because you need a little bit of string to tie it around itself as well and stuff like that. So let's say that you have the higher extreme at 90 centimeters and the upper extreme at 10 centimeters. So we want to have a big range of values between 10 and 90 centimeters, not values that are clustered together like 40, 45, 50, 55, 60, 65. No, we don't want them to fall within a short range of values. Okay, now when I measured y during my board exams, I found y to be 14.2 centimeters, 12.3 centimeters, your 10.5 centimeters, 6.9 centimeters, 5.0 centimeters, and let's say for 7 it would have been 3.7 centimeters. Right, now we just calculate 1 by n, just put them in a calculator, or you can do them mentally. One more important thing that it is that is imperative to note here is the significant figures. Whenever I am calculating data, okay, that's a very important point here. Sorry, that is a very important point here, that is significant figures of calculated data must be same as raw data. Now, what do I mean by this? So if you notice, our raw data is basically measured data. Okay, so in what I have measured, the highest number of significant figures is for y, that is 3, right? The significant figures for 14.2 is 3. That means all my calculated values must be at least 3 significant figures. Over here, we have been explicitly told to have exactly 3 significant figures, but when they don't specify, you should use at least the minimum number of significant figures should be equivalent to the highest significant figures in your raw data. Okay, the safest option in most cases is 3 significant figures. So when confused, go for 3 significant figures. Okay, so I'm just going to record my values here: 1.00, 0.500, 0.333, 0.200, 0.167, and 0.143. Now again, y by n, I just calculate that. That comes to 14.2, 6.15, 3.50. That comes to 1.38, 0.833, and 0.529. Okay, so this is our entire table that fetches us 9 marks. 5 marks are for your values, your 6 sets of readings. Then 1 mark, is for your column headers. 1 mark is for your good range of values, and the next remaining 2 marks are for your significant figures and your calculation. Alright, on to our next question. The graph question. Plot a graph of y by n on the y-axis against 1 by n on the x-axis. That is what the question asks us to do. Now, for graphs, what do? We line up the axes. So this is the y-axis, and this is our x-axis. Okay, we mark the origin, and we choose a proper scale. Okay, we choose a proper scale. Let me just annotate that into our key points. So we have for graphs, point number 8, graphs, we need axis, origin, scale. Okay, so how do we mention that? So the scale, so if we see for the 1 by n on the x-axis, we have values from 0.143 to 1.00. Okay, so that means approximately from 0 to 1. So if you just calculate this over here, there are 8 big squares. That means 80 of these small little squares. It is really indistinguishable on this computer screen, but on a printout they will be easy to make out. Okay, so I am not really going to calculate 10 squares and mark them right now, but then let's just say that this is 1, this is second small square, big square, third big square, fourth big square, and fifth big square, let's say. Okay, so now I am going to select a scale of 0.200 for 1 big square. So this is 0.200, this is 0.400, this is 0.600, this is 0.800, and this is 1.00. Okay, and now I label my axis. This is 1 by n. Okay, now similarly, if I count, there are about 12 big squares on the y-axis, and my values are from 0.529 to 14.2. What do I do in this case? I just take, say, 14.2, right? So I can take a scale of 2 for 1 big square. So let's say this is 2, this is 4, this is 6, this is 8, this is, let's say, 10, about 12, 14, let's say this is 16. Okay, so we have our axis labeled right here. I will give my axis the title label, that is y by n, and the units. Very important to have your axis labeled with appropriate scales. Next, I will write the scales explicitly. Scale. So y-axis 1 centimeter is equal to 2 centimeter. X-axis, the scale is 1 centimeter equals to 0.200. Right? 1 centimeter is basically your 1 big square. Okay, so I have written my scale. Next, I will start plotting the points. Okay, so 1 by n for 1, it is 14.2. So let's say for 1.00 it is some 14.2. So should be somewhere here, right? I'm not exactly, checking the bars right now, but I think you get the point. Okay, now when you're plotting these points, make sure that the points are small enough. So if, for example, I want to make a point here, my point should not exceed the boundary of the 4 adjacent squares. Okay, so my square should be within the adjacent 4 squares. So let's say that the next point was about 0.5, 6.15. So somewhere here again. Then the next point somewhere, let's say, here again. And then you had a point here, let's say. You had a point maybe here, and then another point, let's say, over here. Okay, so you have 6 points right now. This is how your points look. Now the next thing that you want to do is make a line of best fit. How do you make a line of best fit? So for a line of best fit, okay, let me clear that up. For your line of best fit, LOBF, you want to have maximum points passing through the line, and secondly, you want to have equal points or almost equal points either side of the line. Okay, so what does that mean? Let's say that my line of best fit, and I'm drawing this freehand without a ruler on a graphics tablet, so my line would be pathetically wrong. I agree to that, but I hope you can get the hang of it. Okay, so let's say that my line of best fit looks somewhat like this. Okay, somewhat like this. Okay, I'm sorry for the horizontal bars there, but yeah, somewhat like this. Okay, this is how my line of best fit looks like. So it passes through the point over here and the point over here, and then 2 points to the left, 2 points to the right of the line. This is a quite well spaced out line of best fit. Okay, now the next thing that you want to do. Okay, so the questions D1 and D2 have been answered. Question number D3, determine the gradient and y-intercept of this line. Now, to determine the gradient, we need to find out 2 points, where the line is passing through. So let's say I take this point, okay? This point, which is 1.00, 14.2, okay? And let's say that I have another point, okay? I'll just use my script to find out what the other point that was. Yeah, let's say we have another point over here somewhere. Okay, let's say that this is 0.2 comma 1.4. Okay, these are 2 points that we have. Now we want to join these points. Okay, you want to make a triangle joining these points somewhat like this. Okay, this shows the examiner that these are the 2 points that you have used, and this is how we will be calculating the gradient. Okay, so the gradient is equal to delta y upon delta x. So you just calculate the difference in the y coordinates. So the y coordinates, the difference will be, say, 14.2 minus 1.4. So if we just take our y coordinates, the gradient was 14.2 minus 1.4, and the difference between the x coordinates is 1 minus 0.2. You can just take a look at the coordinates over here, right? So that gets us to 12.8 upon 0.8, and if I calculate that, my gradient comes to 16.0. Now take care, guys, take care. I have written 16.0 and not 16. This is given to 3 significant figures. Very, very important. Okay, if you forget the significant figures, give it to 2 significant figures, you drop a mark automatically. Now for the y-intercept, we will be using a formula that is y equals to mx plus c. Okay, in the y substitute any y value. So let's say I substitute 14.2. Okay, m stands for gradient, so I'll substitute my gradient over here, and x stands for the corresponding x value. So if I take the y value on the left, I take the x value on the left, that is into 1 plus c. So c is 14.2 minus 16.0. c is minus 1.80. Again, 3 significant figures. So 16.0, negative 1.80, and we have solved our question D3. Okay, next question. It is suggested that these quantities y and n are related by the equation y by n is equal to p by n minus q, where p and q are constants. Using your answers in D3, determine the values of p and q and give appropriate units. Very simple, guys. That is, in this particular question, it is always one value is going to equal your gradient, another value is going to equal your y-intercept. Always. Okay, so I can rearrange this as y by n is equal to p 1 by n minus q. Now, if you notice, guys, in our previous equation, y by n, this y by n is plotted on the y-axis, and 1 by n is plotted on our x-axis. So this is almost equal to the equation y equals to mx plus c that we have had over here, this equation, right? So what we will say here is p equals gradient, and be careful, guys, this is minus q, okay? So minus q is equal to y-intercept. Okay, so now if I just sort of get my values correct, so p will equal 16.0 and q will equal negative of negative 1.80, which is 1.80. Now the catch here is appropriate units. So if I just find out the units, how will I find out the units here? Gradient is equal to delta y by delta x. What is y? Y is y by n. If you look at our table over here, y by n has the units of centimeter, right? Y by n has units of centimeter, whereas 1 by n has no units. Okay, 1 by n has no units. So it is centimeter upon no units. So it is just centimeter. So gradient has the unit of centimeters. So P is 16.0 centimeters. Now if we look at our y-intercept, the y-intercept will always have units as the other terms in the equation. So the unit of y by n is the unit of q. So y by n has units of centimeters, so q is 1.80 centimeters. That is how we will be solving this question. Now, whenever you get these kind of questions, it is just algebra manipulating the terms and finding your values. So if I need to find the value of r, I need to make r the subject of the formula. So p 18m plus r is 9ma. This is what we can write. 18m plus r is 9ma by p. 18m r is 9ma minus 18m by p. Okay, 9ma upon p minus 18m. Now if we just substitute the values, we are given that m equals to 10, a equals to 48.1, we found that out at the start of the paper, and p is 16.0. If we just put this into our calculator, we will get r equals to 90.6 grams to the nearest 3 significant figures. That is our 20 marks at the start of the question. Okay, well done. If you've made it till here, let's go to the shorter question, which is, easier to perform, but it is full on analysis and it contains the 8 marker credit question at the last, which we will be discussing in depth when we get to it. Okay, for now, let's just follow the instructions and play along. So, set up the apparatus as shown in figure 2.1. The rubber band should be straight but not stretched. The distance between the ends of the rubber band is L0 as shown in figure 2.1. Measure and record L0. Okay, so simply, if you look at the diagram, one very important detail that we see is that L0 or L0 starts from the top of the top clamp and the bottom of the bottom clamp. Okay, it is not from the middle of the clamps. So that is one very important detail that we need to keep in mind when we are measuring the values of L0. Okay, so when I measured it using a ruler, I found L0 to be 16.2 centimeters. Now, estimate the percentage uncertainty in your value of L0. Now, this brings us to our next key point, that is accounting for experimental uncertainty. Okay, so when you measured this L0, you use the ruler, right? You put the ruler here. Sorry for that bad drawing. But you took the you in your mind you calculated L0 say as the top value, the top reading of the ruler minus the bottom reading of the ruler, right? So L0 was top minus bottom. We know that the ruler, for a ruler, the absolute uncertainty is 0.1 centimeter, right? So absolute uncertainty is 0.1 centimeter. But since we are taking two readings, the absolute uncertainty here becomes 0.2 centimeters. However, however, in an experimental condition, you cannot ensure that okay, I have not had any parallax error, my rule is exactly perpendicular to the bench, correct? So there is something called as experimental uncertainty. That means that in our absolute uncertainty, they're also accounting for the fact that we might not have performed the experiment correctly, that the instruments are not properly in place, right? Not just the fact that we haven't taken the readings correctly, but also the fact that the apparatus has not been placed correctly. So for that, we add 0.1 or 0.2 to our percentage uncertainty. Okay, so to our absolute uncertainty. So our actual absolute uncertainty over here will be 0.3 centimeters. Why will it be 0.3 centimeters? It will be 0.2 centimeters of the absolute uncertainty of the ruler and 0.1 centimeter of the experimental absolute uncertainty. Okay, because maybe the ruler is not perpendicular to the bench. Okay, so there is this slight angle. Maybe I have not had eye level. Maybe I'm not taking the reading from eye level. So that gives me another uncertainty. So as many problems as you can spot, you can keep adding a 0.1 centimeter over here for this. But 0.3, 0.4 centimeters is a very safe bet in most cases. Okay. Now the percentage uncertainty, we just simply substitute our absolute uncertainty in the formula. 0.3 divided by 16.2 into 100, which gets us the value of 1.85%. Again, three significant figures if you have noticed. The width of the unstretched rubber band is W0 and its thickness is T, as shown in figure 2.2. Measure and record W0 and T. So again, we had a micrometer that was provided to us. So all we did was just use the micrometer, find out W0 and find out T. So the readings that I got was 0.739 centimeters, and for T it was 0.120 centimeters. Again, if you notice, we have recorded the values to the least count of the micrometer, which is 3 decimal places, and we have included appropriate units. Okay, here you can also use the average thing that I taught you. If you don't, it is not penalized, but if you do, it obviously impresses the examiner even more. Okay, increase the distance between the clamps until the distance between the ends of the rubber bands is approximately 1.5 LO. The distance between the ends of the rubber band is L. The width of the rubber band is W. Measure and record L and W. Okay, so if L is 16.2, don't exactly take 1.5 times of LO, right? Just take like 0.23 centimeters up or above or below. So I got my value of L as 24.6 centimeters, and W over here was 0.645 centimeters, right? Just simply recording the values, nothing too extravagant over here. Calculate delta L and delta W. You have been given the formulas, you just have to substitute and write down the readings. Okay, so delta L is 24.6 minus 16.2, which gives us 8.40 centimeters. Delta W is W0, which is 0.739 minus 0.645. Delta W is 0.0940 centimeters. Okay, 8.40, 0.0940. Now, if you notice, guys, I have added an extra 0. I have added a fourth decimal place to ensure that my delta W value is to 3 significant figures, right? ensuring that my calculated values has the same significant figures as the highest significant figure values of my raw data. Now, see, we have been explicitly asked to give a justification for the significant figures. So what will we write? We will simply say that delta L is correct to 3 significant figures. Why? Because same as the significant figures wait, whatever I written here, significant figures of L and LO, which is the raw data. Very important to use the keyword raw data. So our raw data is L and LO. L and LO are to 3SF. So that is why delta is L is also to 3SF. Okay, next. Increase and the distance between the clamps until the distance of the ends is approximately twice LO. Measure and record L and W. So you simply repeat the experiment. I found the values of L and W to be 32.5 centimeters. W was 0.573 centimeters. Repeat C2, so calculating delta L and delta W. So if I just did the calculations, it was 16.3 centimeters here, and this was 0.166 centimeters. Okay, because it's getting a little too long and I don't want to pester you so much before the exam, let's just say that these are the values that we have calculated. Now, this is another very tricky question, important question. So what do we do here? When we're calculating two values of K, I use the subscripts K1. So K1 using the first value of delta L and delta W, which was 8.40 and 0.0940. So we use these values here. So that K is 8.40 divided by 0.0940. Now, be careful, both the values are in centimeters, so K will have no units. Otherwise, if K had units, I have to specify the units of K that I'm using. Okay, so that comes up to 89.4, 3 significant figures. Again, a calculated value to 3 significant figures. And K2, I use 16.3 divided by 0.166, that comes up to 98.2. Okay, so my first value of K is 89.4, second value of K is 98.2. Now, this is a very important question, okay? This is super important. How do you tackle that? So it is suggested that the percentage uncertainty in the values of K is 25%. Using this uncertainty, explain your values, whether your results support the relationship in E. So first, we find the percentage difference. The formula for percentage difference is K2 minus K1 upon K2 or K1 into 100. Okay, so whichever is larger, you subtract the smaller from the larger. So percentage difference, if I just calculate this over here, I will get that if we just take our values over here, 98.2 and 89.4. So the percentage difference is 98.2 minus 89.4 upon 98.2 into 100. So that comes to about 9.84% if you put that in the calculator. So we have established our percentage difference. But if you leave your answer till here, you get a 0. Now after this, we have 3 very important statements that we need to write. Okay, the first statement is percentage difference is less than percentage uncertainty. That's our first statement. Therefore, K is equal, or K values are equal within limits of experimental accuracy. If it was not equal, it would have been unequal beyond the limit of experimental accuracy. Okay, and so that is why thus we can say results support the suggested relationship. So we have established a suggested relationship. This entire answer will fetch you your 1 mark. The approximate force F acting on the rubber band is given by this, where the Young modulus E of rubber is blah blah blah. Use your second value of K and your value of delta W from D to determine a value of F. Now, in these kind of situations, okay, where in the second question, if you've been asked to determine values, always remember you need to use SI units. So, key point number 11, use SI units for your calculations. Okay, always remember. So, F will now be equal to 2. So, value of E is 1.0 into 10 raised to 6. The value of T, the thickness that we had determined, was 0.120 centimeters. So, if I take that into meters, that would be 1.2 into 10 raised to minus 3 meters. Similarly, with the value of K, second value of K, 98.2, that has no units, so I do not need to worry about that. Then the value of W naught or W0. W naught was 0.739 centimeters. So that again converts to 7.39 into 10 raised to minus 3 meters. And again, delta W, the second value of delta W is 0.166. So that again converts to 1.66 into 10 raised to minus 3, right? Upon L0, L0 is 16.2 centimeters. So in meters, that becomes 0.162 meters. So F, if you just put this into your calculator, I know there's a lot of numbers, but then if you just stop the video, think about this logically, it will all make sense for you. So if you put this in your calculator, this comes up to around 17.8 newtons. Okay, and that is your part G. Now, part H, errors and improvements. So I have made a full video on practical errors and improvements that I will tag here. Okay, please refer to that video. That has all the different the experiments that could come up for your AS level physics practical, right from oscillations to measuring lengths, to different equipment related errors, from cars and ramps and etc, everything. So please go check that out. I am sure that will help you out so much. But here in this equation, in this experiment here, we have to suggest 4 uncertainties or improvements. Now, when I walked into this paper, I was blown away because the only thing that we were measuring was length. Okay, and I was so blank that I screwed up a little bit in this question. But if I had to do it all over again, I would keep my mind a little bit more open to different things, and walk with a broader mind, a more open mind, I could say. Yeah, whatever. So the first source of uncertainty in the short experiment is always going to be 2 results are not enough to draw a valid conclusion. So the solution to that would be take more readings. Now I always give this pro tip of mentioning the variables. Okay, mention the variables in your improvements or errors of L and W, and then plot a graph or compare values of K. So plot a graph of delta L against delta W. Okay, the next problem that we can see was that the parallax error while measuring LO or L. Right, when we're putting this ruler, it is difficult to have the eye level set at the height of the clamps and the bosses. So that is why parallax error might occur. So what do? We clamp the ruler, and then we can adjust our eyesight to a level that is parallel to the height of the boss. So clamp the ruler to a stand. Okay, the next problem that I found when I was performing the experiment was that when I was putting the rubber band between the micrometer screw gauges, the rubber band would bend and squash between the micrometer. That was a big problem for me. So how did I tackle that? Use a traveling microscope. Now if you look at that video of practical errors and improvements, it has, some the apparatus of traveling microscope, all these problems, the solutions are over there, and if you know the solutions, you can sort of implement them to any different problems or any different experiments that they give you. Our paper was particularly tough because there was just lengths and thicknesses and widths that we were measuring. There was no time, there was no weight, there was no force or something that we were measuring. So that really complicated things for us. However, there was a solution that, when you measured the length, the initial length of the string, you didn't know when it was exactly straight but not stretched, right? So difficult to determine when rubber band is straight but not stretched. And the solution to that, the solution was to use a Newton meter. So when the Newton meter returns a constant value, until that time the rubber band is not under tension. But when the Newton meter's reading starts to rise, the rubber band has started to gain tension. So use a Newton meter to ensure or to check rubber band is not under tension while measuring L naught. Okay, so this was our 4 improvements and errors in the procedure for this particular question. However, please check that video out. I'm sure that would be very helpful. I will link it up in the iCard here. Also, if you have been really dealing with a lot of psychological stigma, a lot of fear, a lot of nervousness, don't worry, I went through it as well, but then I made this video particularly for you, for what to do in the last week of the exam, and especially in the final few days before, to tackle that burnout, to tackle that fear. And I please click on the video above, and I'm sure that will help you. I'm sorry for all the technical illegibilities that have happened today, but I really hope that you enjoyed this walkthrough, and I'm sure that you will ace this exam. If you want more videos, please subscribe to the channel and comment down what topics or what kind of videos are you more interested in, and I'm sure to get back to you as soon as possible. Thank you so much. Like the video, share it with as many people as I can, and I will see you guys in the next video. Bye bye.